Alright, this section is going to wrap up Unit 1, Physical Properties of Matter, and it's going to focus on density, something that we now should have a pretty good grasp at. One thing you'll notice throughout this entire semester is that what I try to do is I try to give you a model or a lab or some type of hands-on activity for you to kind of define and get an idea of the new topics that we talk about before I give you the notes, which is a bit weird, but I figure if you can give the definition and figure out the definition yourself, I think we're better off that way. Alright, so the textbook definition for density is the following: the mass of a given substance per given volume of that substance. The idea is that you get amount of stuff, how much stuff can you compact in a certain area, right? Or a certain volume, rather. We can have an equation for density, and this is it. Density equals mass divided by volume, and we shorten that up by saying D equals M divided by V. Obviously mass is going to be measured in grams and kilograms, and volume is going to be measured in things like milliliters and centimeters cubed. And we've got three different common phases of matter that we're going to discuss in this class, and each one of these phases of matter has a different associated unit for density that's most commonly used. Liquids are typically given with the density of grams per milliliter. And to give you a representative example of a liquid that you're familiar with, water has a very nice density of 1.000 gram per milliliter. Solids has a density of grams per centimeter cubed. So if you look at the solids that are on my chart on the right side of the table, you'll notice that most of them reside at the bottom of the table, right here. I'm going to include magnesium, which I just kind of went over a little bit. These all, there we go, these are all solids, so magnesium down through gold. They're solids at room temperature, right? We could make them liquids if we got them hot enough, but for the most part they are solids. Finally, gases. Typically if we have gases, they are going to be given with densities of grams per meter cubed. Grams per meter cubed, just because the gases they have such a low density. You can have a pretty big area that has a pretty small mass, a pretty big volume that has a pretty small mass. So those are the units we give. All right, let's give you some pictorial ideas of density. I'm going to give you two examples here. We have gas, liquids, and solids. And as you can see, as we move from left to right, our density is increasing. All right, we've got the same volume in every single one of these pictures. What changes about each one of these, so we'll call this V1, we'll call that V2, and we'll call that V3. All of those volumes are equal. What changes in each one of these are the number of particles that are packed into that volume. Okay, so the number of particles in 1, in 2, and in 3 are not equal to each other. If the number of particles aren't the same, the one with the most particles has the most mass, the one with the least particles has the least mass, and then this one is in the middle, right? Some goofy shape around it. There we go. So we can define volume, and we can see volume changes based on changing the amount of particles in a defined set volume. We can do that differently. Let's say we have 3 samples, and in each one of these samples we have the same number of molecules, but we look at sample 1, sample 2, and sample 3. Okay, and we would ask ourselves, alright, which one would have the greatest density? Well, I hope you could see that the greatest density is actually to the left. So our arrow would now be in the opposite direction, right? We've got more dense over here, more dense, and less dense over here, less dense. Okay? So density varies based on two different properties. It varies based on mass, and it varies based on volume. When we're talking about its relationship to volume, we have to understand two terms, direct and indirect relationships. If we look at the equation for density, we say that density is directly related to mass. That means if density goes up, mass has gone up. Okay? Density is indirectly related to volume. That means if density goes up, volume's going down. Okay, so if volume goes down, density goes up. Same idea. So this relationship right here we call a direct, and this we usually call an inverse or indirect relationship. Okay? Great. So lastly, I'm just going to give you a couple applications of density. Where do we use this in real life? The first one is antifreeze. You all have antifreeze in your vehicles that you drive, especially with the conditions that we're facing this winter. Antifreeze works by mixing with the water in the car to protect it against freezing. Okay? That's what it does in the winter, at least. The density of a mixture of antifreeze and water actually decreases with a decrease in antifreeze. So if you lose antifreeze, the density of that solution that you've got inside of your engine is going to decrease. The second way that we can apply density is understanding the alcohol content of beverages. If you're a brewer, you use density to find the percent alcohol in the particular beverage that you're making. The idea is that the density before fermentation minus the density after fermentation is proportional to the alcohol content. Not equal, but proportional. So the larger that difference before and after, the more alcohol there is in the beverage. The smaller that difference before and after, the less alcohol there is. And this is the main idea. Sugar water is more dense than alcohol water. Okay, that's how most beverages that are alcoholic start out, as some type of sugary water. Yeast is added to that sugary water. There's fermentation that precedes, and then alcohol is one of the byproducts. The alcohol water is less dense than the sugar water. If we know the difference in densities, we know how much alcohol has been produced. The tools we use to find these two things are as follows. For antifreeze, we use this guy on the left. It's essentially what we call a hydrometer, and you're going to suck antifreeze up the hydrometer in this direction. The antifreeze is going to fill the tube, and there's a little bob in here, and that thing will bob up and down inside of the tube, and wherever the glass bob stops going up and down, we can actually read where the liquid level lines up with that bob, and that will tell us essentially the density of our mixture. And then we can understand if we have to add antifreeze or if we don't have to add antifreeze. And any time that you get your fluids checked, when you get your oil changed at the car shop, at the service shop, they should check your antifreeze level. For measuring alcohol content, we use the same type of tool, but we don't have to suck anything up because we can actually get at the alcohol. So the alcohol would be inside of this little graduated cylinder, or any substance we want to find the density of. And then we place the hydrometer inside of the substance, and it will again bob up and down. It'll go up and down until it settles at some point. And we can actually read the actual density from the graduations that are listed on the hydrometer. And I'll bring one of these into class on Monday and show you how it works with a sugar solution. Alright, that's density.